Today, we're stepping into the heart of one of North America's most impressive steelmaking facilities, Iveco Rolling Mills, located in L'Orignal, Ontario, Canada. And trust me, once you see what goes on inside this place, you'll never look at a steel wire the same way again. It all starts with raw steel scrap, the kind of recycled metal that gets melted down in massive electric arc furnaces, reaching temperatures of over 3,000 degrees Fahrenheit. That molten steel is then poured and continuously cast into billets, those long, square-section steel bars that are the building blocks of everything that follows. Each billet typically measures about 5.5 inches square and can weigh several hundred pounds. These are the starting point. Now here's where the magic really begins. Those billets get reheated in a walking beam furnace, a marvel of industrial engineering that slowly walks each billet through a controlled heat zone, bringing the steel back up to rolling temperature, around 200 degrees Fahrenheit. Why reheat? Because steel at that temperature becomes workable, almost like very stiff dough, allowing the rolling mill to shape it without cracking. From there, the billet enters the roughing mill, a series of powerful rolling stands that progressively squeeze and elongate the steel. Each pass reduces the cross-section and increases the length. We're talking about a piece of steel that starts thick and square, being transformed pass by pass into a long, round rod. The process continues through intermediate rolling stands and finally through the finishing block, a high-speed rotating assembly that delivers the wire rod at its final diameter, typically between 5.5 millimeters and 20 millimeters. At the exit, the wire rod is traveling at speeds up to 100 meters per second. That's roughly 220 miles per hour, and it's coiled by a laying head, which loops the rod into neat rings before it lands on a Stellmore conveyor for controlled air cooling. That cooling rate determines the final mechanical properties of the steel. Slow it down, you get a softer wire. Speed it up, you get higher strength. The finished coils are then collected, weighed, tagged, and shipped to customers around the world, where they become springs, fasteners, cables, and reinforcing materials used in everything from bridges to your car's engine. Iveco has been doing this for decades, and watching it run in full production is nothing short of breathtaking. Now here's something you don't see every day: bending a slab of mild steel that's nearly 2 inches thick. That's right, 2 inches. We're talking about a plate that measures 50 millimeters thick, a full meter wide, and 2.25 meters long. In the old days, shaping a piece like that meant hours of flame cutting, hammering, and grinding. Today, one machine does it in a single controlled motion, and the results are absolutely stunning. The machine doing the heavy lifting here is the HSS 30624R hydraulic press brake, a true workhorse of modern metal fabrication. This beast delivers a bending force of 3,000 tons, with a working length of 200 millimeters. That 4R in the name tells you something important. It means the machine runs 4 hydraulic cylinders working in perfect synchronized harmony. That synchronization matters enormously when you're bending a plate this thick, because even the slightest deviation in pressure across the beam can cause the bend to go off angle. And with steel this massive, there's no room for error. Before a single ton of force is applied, the operator programs the CNC control unit, setting the exact bend angle, the back gauge position, and the tonnage required for the specific material grade. Mild steel at 50 millimeters thickness demands extreme precision in the calculations. Too little force, and the steel springs back. Too much, and you crack the material or damage the tooling. The tooling itself is specially hardened. The upper punch and lower V-die are machined to tolerances tighter than a human hair. As the ram descends, the steel begins to yield, slowly at first, then with a deep, satisfying groan as the fibers of the metal stretch and compress simultaneously on opposite faces of the plate. Watch closely as the bend completes. The operator verifies the angle using a precision gauge. And just like that, a perfectly formed structural component is ready for the next stage of fabrication. It's brute force married to modern engineering, and it's something you simply have to respect. What you're watching here is a beautiful example of how far automated manufacturing has come. Lathes motor assembly line represents the kind of precision and repeatability that would have seemed like science fiction just a generation ago. Let's start at the beginning of this process. That robotic arm is handling the stator core, which is the stationary part of the electric motor. Now, inserting copper windings into a stator used to be a skilled manual operation requiring patience and steady hands. Notice how this automated needle winding system feeds wire through each slot with perfect tension and placement. The robot positions the stator, and specialized needles insert and form the windings in a choreographed sequence that takes seconds per coil. Moving down the line, you're seeing the rotor assembly station. The rotor shaft, lamination stack, and end rings must align within tolerances measured in hundredths of a millimeter. The vision system you see mounted above uses high-resolution cameras to verify positioning before the hydraulic press seats everything together. If something's off by even a fraction, the system stops and alerts the operator. Here's what's particularly clever about Lathes' approach. Each motor is being built with its own digital record. As components move through assembly, sensors and cameras are documenting measurements, verifying torque values on every fastener, and tracking which specific parts went into which motor. The balancing station you're seeing now is critical. Even a slight imbalance in the rotor causes vibration, noise, and premature bearing wear. The machine spins the rotor, measures vibration, calculates exactly where to remove tiny amounts of material, and then precisely mills those correction points. The final automated testing station energizes each motor, measures current draw, checks rotation, and verifies performance specifications. Any motor that doesn't meet parameters gets flagged for manual inspection. This level of automation doesn't eliminate skilled workers. It elevates them to oversight and problem-solving roles while ensuring every motor meets exacting standards. "37 feet long, 28 tons. This is the kind of workpiece that makes even experienced machinists stop and stare. What you're looking at is a port tableau reversing main shaft, the heart of a massive industrial reversing drive system, and it's about to be precision machined on one of the most impressive lathes ever built, the Poreba TCG200. The Poreba TCG200 is a Polish-built heavy-duty lathe with a legendary reputation in shipbuilding, steel mill, and power generation industries. With a swing over the bed exceeding 2,000 millimeters and a distance between centers that can accommodate workpieces well beyond 10 meters, this machine was born to handle giants. Its spindle drive delivers the kind of torque that's measured not in foot-pounds, but in thousands of them. Mounting a 28-ton shaft onto this lathe is itself an engineering event. Overhead cranes carefully lower the shaft between centers. Steady rests are positioned at calculated intervals to prevent deflection, because at this length and weight, even hardened steel will flex if unsupported. The cutting begins with roughing passes, heavy cuts that peel away thick layers of material, shaping the basic profile of the journals, flanges, and keyways. Then come the finishing passes, slower, more deliberate, with cutting tools ground to exact geometry. The tolerances on a shaft like this are often measured in hundredths of a millimeter, a surface finish you can feel with your fingertip. The kind of craftsmanship that quietly holds entire industries together and has for decades. Most of us have never thought twice about the wheel spinning under a heavy machine or an industrial vehicle. We just assume it was cast in a mold somewhere, bolted together, and shipped out. But what Starco does is something far more elegant, and frankly far more fascinating. They use a process called spin forming or flow forming, and once you understand how it works, you'll never look at a wheel the same way again. Here's the idea. Instead of pouring molten metal into a mold or welding separate pieces together, Starco starts with a flat, circular disc of metal. That disc is mounted onto a mandrel, a precisely shaped steel form that defines the final wheel profile. The mandrel begins to spin at high speed, and then the magic happens. Hardened steel rollers press against the rotating disc with enormous force, thousands of pounds of pressure, applied at carefully calculated angles and feed rates. The metal doesn't cut or fracture, instead it flows, literally flowing like cold clay, taking the exact shape of the mandrel beneath it. Wall thickness, flange geometry, bead seat dimensions, all of it is dialed in through the CNC-controlled roller movement. What makes this method superior? For starters, the grain structure of the metal is compressed and aligned during forming, which actually makes the finished wheel stronger than a cast equivalent of the same weight. You get better fatigue resistance, more consistent dimensions, and significantly less material waste. No welding seams, no porosity from casting, just one continuous, seamless piece of formed steel. Starco has refined this process to a level that serves agriculture, construction, and specialty vehicle markets worldwide. It's ancient metallurgy meeting modern precision, the spinning wheel reinvented for the 21st century.